Hello, geometry students. In this video, we are going to continue our Unit 10 notes. So this first theorem has to do with a line L that's tangent to a circle S. So we have a line L. What it means for a line to be tangent to a circle is that it touches the circle exactly once. So also you'll notice in this picture that we have a radius ST that's drawn to the point of tangency. So what this theorem tells us is that when we have a line that's tangent to a circle and we have a radius drawn to the point of tangency, then that radius and that line have a relationship, and the relationship is that they are going to be perpendicular to each other. So if line L is tangent to circle S, then we may conclude that segment ST, the radius drawn to the point of tangency, is perpendicular to line L. Now this theorem is biconditional, so it goes the other way as well. If we have a segment that's perpendicular to a line, a tangent line where that radius is drawn to the point of tangency, then we can conclude that the line L must be tangent to circle S. All right, in the next theorem, we have two segments, segment BA and BC, that are both tangent to circle D. So you can see in the picture we have two segments that are tangent to the circle from the same exterior point, and the conclusion is going to be that those two segments are congruent to each other. So if segment BA and segment BC are both tangent to circle D from the same point of tangency, then we can conclude that segment BA is congruent to segment BC. Our next theorem tells us how to find the measure of angles, angle 1 and angle 2, when those angles are formed by two secants or chords that intersect in the interior of a circle. So in this picture we have two secant lines that intersect right here. Now one thing I want to point out is that this point may or may not be the center of the circle. Now if it happened to be the center of the circle, this theorem would still work out, but generally you'll be looking at examples where you have two secants that intersect in the interior of the circle and that point of intersection is not the center. So let's first of all talk about how to find the measure of angle 1. Well, to find the measure of angle 1, we will use the two arcs that are cut off by angle 1 and also by its vertical angle. And to find the measure of angle 1, the measure of angle 1 will be equal to 1/2 the sum of those two arcs. So the one arc that angle 1 cuts off of the circle is arc AB. So we'll take the measure of arc AB, and then we will add that to the measure of the arc that's cut off by its vertical angle. So that would be arc DC. So we take the sum of the measures of those two arcs, add them together, and that will give us the measure of angle 1. Now the measure of angle 2 then, same idea, we will find the measure of angle 2 by taking the sum of the measures of two arcs, and those two arcs would be arc BC, and then also the arc that's cut off by the angle that's vertical to angle 2, so that would be arc AD. So the measure of angle 2 is equal to the measure of, or 1/2 the measure of arc BC plus the measure of arc DC. All right, now this next example, we have a secant and a tangent that intersect at the point of tangency. So a secant line or ray in this case that touches the circle twice, and then we have a tangent that touches the circle exactly once. That secant and that tangent intersect, and their point of intersection happens to be the point of tangency. So if that's the case, to find the measure of either of these angles, well, I want you to notice where the vertex of that angle is. Let's look at angle 1 first. Notice that the vertex is on the circle, so just like an inscribed angle, to find the measure of angle 1, we will take this intercepted arc and we'll take half the measure of that angle. So the measure of angle 1 would be equal to 1/2 the measure of the arc that it intercepts, so that would be the measure of arc AB. And then the measure of angle 2, we'll find the measure of angle 2 by taking half of the arc that is intercepted by the secant and the tangent. Now that's a major arc, so we're going to name it using 3 points. So let's call it arc ACB. So to find the measure of angle 2, we will take 1/2, oops, I meant to grab a pen there. We will take 1/2 the measure of arc ACB. Now for these next 3 theorems, I want you to notice that we're going to be finding the measures of, in each case, we're going to be finding the measure of angle A. And notice that the measure of angle A, or the angle A, is formed by the intersection of either 2 secants, or a secant and a tangent, or 2 tangents. So in all 3 cases, we're talking about an angle whose vertex is in the exterior of the circle. And generally, we're going to be finding the measure of angle A the same way. So in this first theorem, we have 2 secants that intersect in the exterior of a circle. So if that's the case, then the angle formed, angle A, to find its measure, we will take the 2 arcs that are cut off by those 2 secants. So we'll take arc DE and arc BC, and we will take half of their difference. So in other words, the measure of angle A is equal to 1/2 the measure of arc DC minus the measure of arc BC. All right, now the same kind of idea will happen in this next theorem. This time we have a secant and a tangent that intersect in the exterior of a circle. So we have this angle A whose vertex is out here in the exterior. Now you'll notice that the secant and the tangent intercept 2 arcs. One of them is arc DC and the other one is arc BC. So just like in the last theorem, to find the measure of angle A, we will take 1/2 the difference of those 2 intercepted arcs. So 1/2 the measure of arc DC, and then minus the measure of arc BC. So half of the difference of the 2 intercepted arcs. All right, and then in this third theorem, same idea, except this time we have 2 tangents. Okay, so we have 2 tangents that intersect in the exterior of a circle. So to find the measure of angle A, we will look at the 2 secants that are cut off by the 2 arcs that are cut off by these 2 tangents. All right, one of them is this red arc. It's a major arc BDC. The other arc is BC. So to find the measure of angle A, okay, we're going to take 1/2 the difference of 2 arcs again. So we'll take the major arc, the measure of the major arc, which we're going to call arc CDB, and we'll subtract from that the measure of arc, the blue one, BC. And so the measure of angle A is equal to half the difference of those 2 intercepted arcs. And so for the next 3 theorems, we're going to switch gears. We've been talking about the measures of angles. This time we're going to be talking about measures of segments. So we'll see 3 situations here. Here we have 2 chords that are intersecting in the interior of a circle. The next theorem we have 2 secants that intersect in the exterior of a circle. And then in the last theorem we have a secant, or a tangent and a secant, that intersect in the exterior of a circle. So let's look at these theorems that tell us how to find the measures of these segments. So our first theorem talks about 2 chords that intersect in a circle. So we have 2 chords and their intersection is in the interior of the circle. So we have the following relationship. When 2 chords intersect in the interior of a circle, then they cut each other up proportionally. In other words, we can take the product of AB times BC, okay, so that's the product of the pieces of one chord, and that product will be equal to the product of the pieces of the other chord, which would be EB times BD. EB times BD, okay? In the next theorem, we have 2 secants that intersect in the exterior of a circle. All right, so we have secant AC and we have secant AD. And what this theorem tells us is the following relationship is always true. If we take the measure of one entire secant, which would be AC, and multiply it by the piece of the secant that's in the exterior, so that would be secant A or segment AB, if we take its measure. Okay, so again, we have taken the measure of the entire secant times the measure of the secant just on the exterior part. That's going to be equal to the product of the measure of the other entire secant times the measure of the exterior part of that secant. So in other words, all of secant AE, its measure, would be equal to, we're going to multiply that by the piece of the measure of the piece of the segment that's in the exterior of the circle, AD. All right, so again, the measure of the entire secant times the outside is equal to the measure of the other entire secant times the outside. Now this next theorem, this time we have a tangent and a secant that intersect in the exterior of a circle, but it's still the same idea. It's still going to be the entire segment times the outside part is equal to the measure of the other entire segment times the outside part. The only difference is that this time, since one of our segments is a tangent, then the measure of the entire the measure of the entire segment and the measure of the exterior part are actually the same thing. So in other words, in this theorem, JK squared, that would be the entire secant, the entire tangent times the outside part is equal to the product of the measure of the other secant, which is JM, times the measure of the exterior part, which is just JL. All right, so now let's take a look at a few practice problems so I can get you started on your classwork, so you'll be able to finish it on your own. So now take your classwork, and I'm just going to give you a hint about number 1, and then I'll help you work out number 2. So number 1, notice what's happening here. We have a segment BC that's tangent to the circle because the directions say assume that segments that appear to be tangent really are tangent. So we have a segment BC that is tangent to a circle, and then we have this radius AC drawn to the point of tangency. So that first theorem we talked about today tells us that when we have a radius drawn to a point of tangency, then that radius is going to be perpendicular to the line that's tangent to the circle. So draw a right angle, and now you have a right triangle to work with, and you can use Pythagorean theorem to find x. Same thing is going to be true on number 2. Here we have a tangent segment SQ, and then we have segment RQ, which is a radius of the circle, and it's drawn to the point of tangency. So when we have a radius drawn to a point of tangency, then the radius and the tangent line will be perpendicular to each other. Okay, so now we can use Pythagorean theorem to find x. So the first thing you might want to do is go ahead and label segment segment RQ, okay? This is also a radius of a circle, so its measure would be x, just like this one. So now let's take a look at this right triangle, and let's use the Pythagorean theorem, which says the measure of the hypotenuse, which in this case we'll use our segment addition postulate and call the measure of the hypotenuse x plus 2. So that measure x plus 2, that hypotenuse squared, is going to be equal to the sum of the squares of the two legs, and the two legs are x and 4. So that's going to be equal to x squared plus 4 squared. So again, that was just the Pythagorean theorem. X plus 2 is the measure of the hypotenuse. The measure of the hypotenuse squared is equal to the sum of the squares of the two legs. All right, so now let me just help you a little bit more with this problem. Let's go ahead and square this binomial. Remember, when you square a binomial, you're going to get 3 terms. So these 3 terms would be x squared plus, take the 2 terms, multiply them together and double. 2x doubled will give us 4x, and then plus the last term squared, and that's equal to x squared plus, let's go ahead and square 4 and call that 16. All right, then the next thing you'll do is you've got an x squared term on both sides, so you can subtract that from both sides, and I think you can take it from there to solve for x. Now, in these next three examples, you're always going to see two segments that are tangent to a circle from the same exterior point. So the theorem we saw told us that when you have two segments that are tangent to a circle from the same exterior points, then we may conclude that those two tangents are congruent to each other. So if the tangents are congruent to each other, then their measures are equal. So we can say that x plus 15 is equal to 2x minus 5. So go ahead and solve that equation for x, and then let's see, the directions said to find x. So once you've solved that equation for x, then you're finished with that one. Okay, now let's take a look at number 7. We're actually going to be using that same theorem. We're going to use the theorem that whenever we have two tangents drawn to a circle from the same exterior point, then those two tangents are going to be congruent to each other. So this segment is congruent to that segment. So in other words, segment RC is 3 because segment RD is 3. They're two tangents or two segments tangent to a circle from the same exterior point. All right, so the directions ask us to find x, and then find x given that the perimeter of this quadrilateral is 18. So let's look at this little segment here. Notice that SA and SD are both segments drawn to both segments that are tangent to a circle drawn from the same exterior point. So they are congruent as well. I'm going to go ahead and put one tick mark because I see that this angle or segment is 3. So that means that all 4 of these segments we can put one tick mark on because this segment SD would be 3 as well. Okay, same thing holds for segment TA and TB. TA and TB are segments that are tangent to a circle from the same exterior point. So that means that segment TA, whoops, let me grab a pen. Sorry, segment TA is congruent to segment TB. So we can call segment TB X. And the same thing is true here. Segment UC and segment UB are segments tangent to the circle from the same exterior point, so they both measure x. All right, so I think that's the hint you need to finish this problem. Add all these together. Let's see, x plus x plus x plus x would be 4x, and then 3 plus 3 plus 3 plus 3 is 12, so we would just say 4x plus 12 is equal to 18, and then you can solve for x. Okay, so let me give you a hint for number 9. Notice you have angle x here that is formed by two chords that intersect in the interior of a circle. So we have an angle with x degrees whose center is in the interior of the circle, but it's not the center of the circle. So to find the measure of angle x, if it were the center of the circle, then we would just take the measure of this intercepted arc. But this vertex is not at the center of the circle, so to find x, you will take half the sum of the two intercepted arcs. So let me highlight those for you. So this arc and this arc, to find x, you'll take half the sum of those two intercepted arcs. So that's a hint for that one, but let me help you work out number 10. So we're asked to find angle x, so that means what we need to do is we need to take the sum of the two intercepted arcs. Now the two arcs I'm talking about is the arc that the angle with x degrees intercepts, and then the arc that its vertical angle intercepts. So whatever x is, it's going to be half of the sum of those two arcs. Well, we don't know what either of these arcs are, what their measures are. However, we can use the fact that this arc is 55 and this arc is 75. And so let's just add those together real quick. 55 and 75 is 130. All right, and since 360 minus 130 is 220, what that tells us is that 220 is the sum of these two red arcs or pinkish arcs. All right, so to find the measure of angle x, then the measure of angle, or not angle x, but the x degrees, x would be equal to 1/2 the sum of the two red arcs. Well, we know that the sum of the two red arcs has to be 220. And then you can take it from there. And then for numbers 12 and 13, notice that they both have a tangent and a secant, who intersect at a point of tangency. So we're talking about an angle whose vertex is on the circle. If the vertex is on the circle, then you find the measure by taking half of the intercepted arc. So to find the measure of angle P, just take half of this arc. And then for number 13, we're told what the measure of angle D is, and you're asked to find the measure of arc FD. So just use the fact that this is an angle whose vertex is on the circle, so that 64 degrees would be half the measure of this intercepted arc. Okay, so let me give you some more help on the back of your classwork worksheet. So the first one asks us to find the measure of angle L, which is an angle formed by two tangents from the same exterior point. So notice that the vertex of that angle is on the exterior of the angle. So the measure of that angle, okay, would be half the difference of the two intercepted arcs. The difference of the measure of this red arc and the measure of this blue arc. So to find x, which is the measure of our angle, it would be 1/2 the difference of the two intercepted arcs. So you'll notice that we know the smaller arc is 102. So now to find the measure of this red arc, notice that the red arc and the blue arc together make up the entire circle. So to find the measure of that red arc, we're just going to take 360 and subtract 102. So I'll let you do that. Put that answer right here, and then do the arithmetic to find x. Okay, and then let's take a look at number 15. This one says find the measure of arc. Oops, it looks like I'm missing. Let's add the arc symbol. We're missing this arc right here. So this time we know the angle, but we need to know the measure of the arc. So notice that this angle A is formed by a secant and a tangent, so it's another angle whose vertex is in the exterior of a circle. So this 56 degrees comes from taking half the difference of this red arc minus the blue arc. So let's go ahead and call the red arc x, since that's what we're being asked to find. And what we're going to do is use the 56 degree angle, which is found by taking 1/2 the difference of the intercepted arcs. So that would be 1/2 of x minus 95. All right. And so let me just help you a little bit more. On this problem, to solve for x, the first thing you'll want to do is get rid of this 1/2, and we can do that by multiplying both sides by 2. So let's multiply this side by 2 and this side by 2. All right, so we would get, let's see, 2 times 56 is 112, is equal to the 2 and the 1/2 will cancel. So that's equal to x minus 95. So I will leave it to you to finish that one. But let me go ahead and help you set up number 16. So again, this is an angle. We're going to use this angle V that is formed by two secants that intersect in the exterior of a circle. So we have an angle whose vertex is outside of the circle, so its measure, this 25 degree angle, is half the difference of the two intercepted arcs. So in other words, 25 degrees is equal to 1/2 the difference of the two intercepted arcs, and you always want to take the bigger arc. That would be the 110 degree angle, or the 110 degree arc, minus the smaller arc, minus x. So again, start this one like we did last time, multiplying both sides by 1/2, and then solve for x. Numbers 17 and 18, we're going to be, instead of finding measures of angles or chords this time, or excuse me, measures or arcs, we're going to be finding measures of segments. So we need to find this missing measure x. So we'll use the theorem that tells us that when two chords intersect in a circle, then the product of the pieces of the measures of one arc is equal to the product of the measures of the pieces of the other, I think I said arc, I'm sorry, I meant chord. So in other words, 6 times x is going to be equal to 4 times 15. So I'll let you write that equation and solve it. But let me give you some help on number 18, because there's just the same idea, but there's a little more algebra involved. So we have two chords intersecting inside of a circle. So the product of the pieces of one chord would be equal to the product of the pieces of the other chord. And of course, when I say pieces, I mean the measures of those pieces. So let's start with this chord ZX. Let's take the product of the measures of the pieces. So that would be x times 6, or excuse me, x plus 6 times x plus 2. So we'd have x plus 6 times x plus 2, and that's going to be equal to the product of the pieces of the other chord, so that would be x times x plus 12. So x times x plus 12. So let me just help you a little bit with the algebra. We need to multiply a binomial times a binomial here, so that's going to be a total of 4 multiplications. So let's start by taking x times x and x times 2. We're going to distribute the x. So we would have x squared plus 2x, and then plus, now let's distribute the 6. So we'll take 6 times x and 6 times 2. So that would be 6x plus 12. And then on the right side of the equation, let's distribute again. Let's take x to get rid of those parentheses. So we would have x squared, we would have x squared plus 12x. All right, so this looks like we're gonna need to solve a quadratic equation, but you'll notice we have an x squared term on both sides, so we can go ahead and subtract an x squared from both sides, and then this problem becomes pretty easy. All right, and then let's take a look at this next one. This is kind of an interesting problem. Did you know that the true shape of a rainbow is actually a complete circle? However, we see only the arc of the circle that appears above the Earth's horizon. So in other words, this rainbow is actually an entire circle, but we don't see the whole circle because the Earth's horizon gets in the way. So what we're going to be asked to do then is we're asked to find the radius of the circle containing the arc of the rainbow shown below. So why don't we draw a smaller picture so we can kind of see the whole picture. So here's the entire rainbow. Oops, what happened to my circle? Let me fix that. Here's the entire rainbow, okay? And then we're given this chord that measures 5 miles, and we're given part of a radius, okay? So what we're missing, what I'm going to do is I'm actually going to draw, let me do it in a different color. I'm going to draw the rest of the entire diameter. Here would be the center of the circle, okay? So what we're being asked to find is we're being asked to find this radius. So what we're going to do is let's label first of all what we know. This entire chord is 5 miles. We have a radius that's perpendicular to a chord. So remember, if a radius or a diameter is perpendicular to a chord, it bisects the chord. So let's call this piece 2.5 miles, and this piece is 2.5 miles, okay? And then we know that part of the radius is 0.7, so let's label that 0.7. And then let's call this piece of the diameter, let's call it x, okay? So now what you see is you see two chords that are intersecting inside the interior of a circle. So we know that the product of the pieces of one chord would be equal to the product of the pieces of the other chord. So in other words, we know that 0.7 times x is equal to 2.5 times 2.5. Okay, so I just took this piece times this piece, the product of the pieces of one chord, and set it equal to the product of the pieces of the other chord. Okay, so I'll leave it to you. You might want to grab a calculator for this one. You'll want to solve for x. When you solve for x, you have part of the diameter. Add 0.7 to x to get the entire diameter. But then remember, you're asked to find the radius of the circle. So once you find this entire diameter, you'll take half of that to get the radius. And why don't we go ahead and say, let's round that answer, round to the nearest, let's say 1/10 of a mile. And then numbers 20 and 21, we have in number 20, we have two secants. 21, we have a tangent and a secant. So we'll use those last two theorems that talk about how to find the measures of these secants. And the first theorem said that the measure of an entire secant times the outside part would be equal to the product of the other entire secant times the outside part. So in other words, for number 20, we would say I'm just going to go ahead and call it 19. Whoops. Sorry about that. The measure of the entire secant, which is 19, okay, times the outside part. So 19 is the entire secant. The outside part is 7. Is equal to the product of the other entire secant, which is x plus 6, use your segment addition postulate, times its outside piece, which is 6. All right, so go ahead and solve that for x, and you'll be done with 20. And then number 21, same idea in general, except for this time, instead of two secants, you're looking at a tangent and a secant. So it's the same idea. You take the entire segment times the outside part. Well, for this tangent, the entire secant and the outside part are the same thing. So we'd have 8 times 8, or 8 squared, is equal to the product of the other entire, the entire secant, which is 7 plus x. 7 plus x times the outside part, which is just x. All right, so this one is a quadratic equation. Oh, let me give you a hint on this one. It's a quadratic equation, but it's not a very pretty one. You will need to use the quadratic formula on this one because you'll have a quadratic that's not factorable. All right, so if you need any help on the classwork, be sure and ask me. And then when you finish with the classwork, you can go ahead and get started on your homework that's posted in Google Classroom.